Hello there, and welcome to another number theory video. So in this video we're going to be focusing on another special number that definitely comes up in a variety of places unexpectedly, and that is what we call the golden ratio. So let us consider a line segment. And let us cut this line segment into two pieces. So there's going to be some point here. So therefore there's going to be two lengths x and y, and let us mandate that this length x is greater than y. So we say that these two lengths are in golden ratio. Some may look at it in the perfect ratio, if you may. So x and y are in the golden ratio if the following thing is true. So the ratio of x plus y to x, so the total length of the segment with respect to the largest length, is equal to the largest length with respect to the smallest length. So if this is true, we say these are in the golden ratio and denoted by Greek letter phi. So in this video, we're going to explore a couple examples and derive what this value is equal to. Alright, so let's work through an example and see if we can generate what the golden ratio for a particular segment actually is equal to. And some people usually built a lot of architecture back in the old days that if you built everything in this ratio, pretty much everything looked perfect, at least to the eye, right? But we're not going to get into the historical details of the golden ratio. So what value of y is going to make these two line segments in what we call the golden or perfect ratio? So this value of y and the value of 3 must satisfy 3 plus y over 3 is equal to 3 over y. And this is going to be equal if and only if 3 and y form a golden ratio by definition, right? Ratio, not ration. Right. So let's figure out what y this is. So this is just a basic rational equation which we can solve. So this is just going to be equal to 3y plus y squared is equal to 9. No big deal there. Which is just the quadratic equation, y squared plus 3y minus 9 is equal to 0. And clearly, from this picture, we're going to assume that y is greater than 0, right? So we're just going to choose the positive of the two solutions to this equation. All right, so y is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, right? So notice here I can factor out my 9 and pull out a 3. So I'm going to have y is going to be equal to negative 3 plus or minus 3 square root of 1 plus 4, which is going to be 5, all over 2. So I have y is going to be equal to, I'm going to factor out a 3 here, so I'm going to have 3 times negative 1 plus or minus the square root of 5 over 2. And remember that this number is positive by assumption, so that's going to be negative 1 plus the square root of 5 over 2, right? Because the square root of 5 is just slightly bigger than 2. And negative 1 minus square root of 5 for sure is going to be negative. So we have that y must be equal to 3 times negative 1 plus the square root of 5 over 2. Great. So remember that x and y form a golden ratio if x over y is equal to x plus y over x. And we found the y that made this true for a particular value x is equal to 3, right? So if x is equal to 3 and y is equal to 3 times negative 1 plus root 5 over 2, then they form this golden ratio, right? And we define this ratio to be 5. So let's actually see the numerical value of that ratio, shall we? Alright, so x is equal to 3, and y is equal to 3 times negative 1 plus the square root of 5 all over 2. So it's very easy to see these 3's cancel, and we can reciprocate this fraction on the bottom. So we're just going to get phi is equal to 2 divided by negative 1 plus the square root of 5. So what I'm going to do is I'm going to rationalize this expression. So I'm going to have negative 1 minus the square root of 5 top and bottom, right? And then I'm going to use my difference of squares relationship to express the bottom in nicest terms. So I have 2, and I can factor out a negative there, and write this as 1 plus the square root of 5, all over, so negative 1 squared is going to be 1, and minus the square root of 5 is just going to be 5. So this is just going to be equal to negative 2 times 1 plus the square root of 5 all over negative 4. And these negatives sort of cancel out very nicely, and I just have phi is equal to 1 plus the square root of 5 all over 2, right? So this is the ratio of these two numbers, x and y. Very beautiful. Now, is this always going to be true regardless of the values of x and y that we choose, as long as they form this quote-unquote golden ratio? Because I've only sort of proven it for this particular case of y is equal to 3. So let's actually figure out if this is the only possible value for the golden ratio, right? And if you want to try this proof out on your own, you can. But we're trying to prove that the unique value phi is always 1 plus the square root of 5 over 2, regardless of the value of y we choose. Alright, so proof. So we're going to let x and y both be positive numbers, and let's assume that they're not 0, because those wouldn't form a golden ratio, obviously, because you can't divide by 0. Alright, so if these form a golden ratio, then that means, by assumption, so we're going to let x plus y over y be equal to x over y. Therefore, x and y form a golden ratio, right? So let's solve this equation for something, right? Oh, and this bottom has to be x, right? By definition. Okay, cool, let's cross multiply and get something out. So we have xy plus y squared is equal to x squared. And let's write this as a quadratic in terms of y. It doesn't really matter. So this is going to be y squared plus xy minus x squared is going to be equal to 0. And let's solve for y. So that's going to be my focus here. You can solve for x and get the equivalent thing if you want. So y is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So we have y is equal to negative x plus or minus, we have x, then we have 5 all over 2. So we can factor out an x. So you can see this proof is sort of following the same exact flow as the actual numerical example we had. So we have x times negative 1 plus or minus the square root of 5 over 2. And by assumption, x and y are both positive numbers, and there's only one value that this can be positive, right? So we're going to choose the positive version of this. So that means y must be equal to x times negative 1 plus the square root of 5 over 2. Great. So we already know that the golden ratio is the quotient of x over y by definition. So x is just some arbitrary number, and the y that sort of forms that golden ratio with x is just going to be equal to x times negative 1 plus the square root of 5 over 2. Regardless of the value of x that I've chosen, x is going to cancel, and we're just going to be left with 2 divided by negative 1 plus the square root of 5. And this puts us back exactly where we were before, so we're just at 1 plus the square root of 5 over 2, right? So this is the golden ratio that we sought out to prove. And as I said before, this comes up in a variety of places, but this theorem and video is just focusing on what is the golden ratio, what is its value, and how do you prove that that is the only value that it has. Anyway, we'll look at applications and occurrences in the next video. Hope you enjoyed.